Okay, so we're recording here. These questions I actually didn't give to you. I think a lot of these are, I think I've stolen them from other things and whatnot, but anyway. So I'm gonna start with, so you don't have access to this final. This is the final from last fall. If I remember, I'll post this one as well, but I mean, at this point, you'll have plenty of finals to study. Giving you one more is not really gonna help, I don't think, unless somebody wants to spend their entire life just working old finals. And at some point in time, it's better to just spend your time, learning the material. Okay, so here's what we got for given. Okay, given. Okay, really? Okay, so I give you this this thing, and it's kind of on an angle, and there's a pump. Okay, and then what comes out of the other side is narrow. I'm not drawing this exactly right because obviously there should be some holes here where the manometer comes in, but doing the best I can here. Okay, and so this is D1, which I think it gives as 2 inches, and then D2 is 1 inch. Let's see. Oil is pumped up and through the contraction shown at a flow rate Q. There's a certain number of CFS. So I don't really know what a good number is for the CFS. I think because everybody got different numbers here, people just got huge answers here. I'm going to go ahead and go with 0.1 CFS because this is a pretty small pipe. Okay, so manometer is filled with mercury. And so we've got mercury from here down to here. If you haven't figured it out, these are pretty much my favorite types of problems to ask, simply because, makes you have to know all your fluids to do these. So they give you that this is H naught equals, okay, this is mercury. So S equals 13.6 or 13.55. So this is 6 feet. That's quite a good bit of pressure considering it's mercury. How much power? Okay, so required, we want power. So the rate of work. How much power does the pump need to supply the fluid? So this is to the fluid. So this is not the amount that you need to supply to the pump. And so all of this, by the way, this is oil. So it has a specific gravity of S oil. So S oil equals 0.82. Okay, you may assume there's no head losses. Okay, so there's no head losses. All right, so this is as you guys know at this point, this is pretty much one of my absolute favorite problems. It did also tell you that this to this, not that this matters, it was just kind of a way to help people define variables. It kind of gave you these heights right here. So this is capital H, and this is lowercase h. Those heights are, you could call them whatever you wanted to call them. In fact, for lowercase h, I would just call it Z2 minus Z1. But sometimes people would like to have a lowercase h because it, instead of having a Z, it's just a smaller term. All right, so what we're going to do here is for the master, I guess this is all part of the given. Okay, so what we're going to do is, well, by the way, one of the red herrings that will show up in a lot of these problems is they'll give you this angle right here. They'll be like, oh, here's this angle, it's like 30 degrees or something. But you don't care about that because all the distances you've been given or not given are vertical. So the only thing you care about is the vertical distance. The only way you would want that angle is if it only gave you a diagonal distance and you need to calculate a vertical distance. Anyway, so we're going to do, we'll do energy equation, P on gamma. And this is obviously energy equation because we've got a pump here. Anytime you see a pump, and what we're looking for here is a power supplied to the fluid. So we're going to be, clearly at that point, we're going to be working with energy equation. And the other way, sorry, before I write out the full energy equation, the other way is to note that the equation we're going to end up with is the power to the pump, not the pump, to the fluid. Okay, if we just remember kind of where we're aiming here, is that the formula for that is gamma HP Q. Okay, so that's the amount of power that the pump is doing on the fluid. Okay, and we know the gamma because they gave us the specific weight. And we know Q. Wait, do we know Q? Yeah, we do know Q. So all we need to figure out is HP. So, no, bull, good. More people. All right, so what we're going to do is we're going to go from 0.1, which I'm going to put right here. So that'll be 0.1. This will be 0.2 right here. Okay, and I'm choosing those points because that's where the that's where the the manometer connects. So that's where we have information. So I'll do P1 over gamma plus Z1 plus alpha V1 squared on 2G plus HP equals P2 on gamma plus Z2 plus alpha V2 squared on 2G. And for space, I'm not going to write out the turbine. I think at this point, everybody knows that, we can scratch out the turbine term. And then there's a head loss term, but part of the problem statement for this one was ignore the head loss. So we're going to ignore that too. Okay, so we'll start by, I use blue for this as we kind of walk through. So P1 and P2, these two are going to have to come out of the manometer. Okay, so maybe we'll do that over here. We'll do my asides over here. It's just, we'll go in order, I guess. So we're going to start at 1. I'll say, okay, well, P at 1. Then I'm going to add, we're going to go down H. So we'll go plus gamma oil times capital H. Okay, and then let's see. So then I'm going to go down and over. All right, but all we care about is it going down. Sorry, that H naught should have been, whatever. It's supposed to align with that. It's a bad drawing. Okay, obviously if it aligned with something else, we wouldn't be able to solve the problem. So we're going to add gamma mercury times that 6 feet, which I'll just call H naught for now. And then we're going to go back all the way up, 1, 2, 3. So we're going to go minus gamma oil, okay, times what's that, 6 feet, or, well, sorry, we're not doing 6 feet yet.
6 plus 8 plus lower H equal to 2.
Right. So, so we'll do H naught plus H plus lowercase h. It's annoying having all those H's, right? So it equals P2. Okay, so we'll bring P1 over, minus P1. Okay, so that gets rid of this thing. And then, and I mean, this is an error that I see people do is to remember that in this equation up here, this gamma in the energy equation, that's the gamma of the fluid that's flowing from 0.1 to 0.2. So that's the gamma of oil. So in this equation down here, we need to make sure that when we divide by the gamma of oil. So that's going to cancel out this gamma oil, and that's going to put a gamma oil under here. Okay, so then the last thing is I've got a positive H right here. I've got a negative H right here, so those are going to cancel. So my equation looks like, let's see here, gamma Hg, which I'm going to write as SHG gamma water over S oil gamma water. So those gamma waters will cancel, times H naught, minus H naught minus H equals P2 minus P1 over gamma oil. Okay, and that's pretty much what it looks like. And, it's a little annoying. We could make that SHG over S O. Anyway, let's go ahead and let's put some numbers in there actually. So let's do SHG, which is 13.6 over SO, which is 0.8 scratched over it. I think that was an 8.6. It's an 8.6 or an 8.2? 8.2. Okay, so it goes 0.82. And then we've got an H naught, which is 6 feet. Okay, minus 6 feet minus H. Okay, so this is a little bit sloppy because I'm not going to work up. Let's get a calculator here real quick. 13.6 divided by 0.82 times 6 minus 6 equals 93.51512 feet minus h. Okay. So that's a pretty nice term. Okay, it's pretty straightforward. Again, this all comes out of the fact that, you know, it's like, why is this number so big? Well, we've got 6 feet of mercury, right? So that's a tremendous amount of pressure, right? So just something to always kind of think about. I mean, we've also got 6 feet of oil on this side, but that doesn't really matter, right? Who cares? And then we've got this extra H over here, but you know, whatever. Anyway, okay, so, all right, so that's going to take care of P2 minus P1 over gamma. So that's P2 minus P1 over gamma oil is on this side of this equation. Okay, so now we need to do Z1 and Z2. So the best way to do that is to, you know, we want to figure out where our datum is. So we'll make this our datum. Okay, so Z1 is 0 and Z2 is lowercase h, which I don't even, oh, here's lowercase h. I was like looking for it. Okay, so this one's going to go away. And this one's going to become lowercase h. And let's see, now we've got V1 and V2, and the way we always deal with those is with continuity. So I'm going to go ahead and delete this work on the bottom so that I can use continuity. And as some of you have noted, you could solve for, you could like put Q directly in if you wanted to just, you know, if you didn't want to do it the way that I do it, that would be fine. But, you know, I don't particularly like that very much. So we have Q. So say Q equals V1A1 equals V2A2, because, you know, everything that flows past 1 has to flow past 2. So we know Q, so we can solve for V1 and V2 pretty straightforward. What I'm actually going to do here, I'm going to use the fact that I know that this is a 1-inch pipe, this is a 2-inch pipe. So I know that V2 is going to be 4 times V1 because it's going to have 1/4 the area. So if you have 1/4 the area, you have to have 1/4 the volume. If you don't want to do that, you can always just solve this equation twice. So 0.1 CFS equals V1 times the area of 1, which is going to be pi times 2 over 12 feet squared over 4. Okay, and so V1 equals whatever that is. Let's see. 0.1 times 4. What's that, times 36? Times 36 divided by pi, I think is right. So V1 is 4.5837 feet per second. Okay, unless I've made an algebraic error there, which of course is always possible. So you can do that twice if you wanted to get V2, or you could just use this relationship right here and take that number and multiply it times 4, and you'll get V2 equals 18.335 feet per second. Okay, so here we go, 1 and 2. Let me turn on the fan real quick. Okay, so, all right, so now we know V1 and V2. For both of these, we should probably get a Reynolds number, you know, because we want to know about alpha here. If you're in a rush, highly recommend just assume alpha is 1.0. Maybe come back to the problem at the end and check it. It's usually a fair assumption. In this case, I can tell you right now, it's going to be fine. But let's go ahead and do it just to be sure. So we'll take this one and this one, and we'll do the Reynolds number. So Reynolds number equals VD on nu. So the V is 4.6. Diameter of the pipe is, so this is at 0.1. So diameter is 2 inches, 2 over 12. Okay. And the viscosity, what I recommend you guys for viscosity, especially because you're at home, I'm going to go ahead and type it in here just so you can't really see it. I recommend the engineering toolbox. If you go to engineering toolbox, viscosity of water, and you just scroll down, you'll see. So in this one, we're in the imperial or the British units. We probably should just call them American units. But I'm going to go to 50 degrees Fahrenheit, and it's going to say that the viscosity is 1.4. 1.4 times 10 to the minus 5th. Okay. And if you wonder which viscosity to use, you need to make sure that the Reynolds number comes out unitless. And so right here, we've got feet per second. Right here, we've got feet. And if you look this thing up, it's feet squared per second. So that means it's going to come out unitless. Anyway, well, let's go ahead and do it just to. So the other thing I actually kind of recommend here is I wouldn't even bother with this 1.4. I'm going to do it since I've already written it down, but it doesn't matter. Okay, we're just trying to get an order of magnitude here. So 4.6 divided by 6 divided by 1.4, -5, and we get 5.5. 5.5 times 10 to the 4th, okay? And in order for this to be turbulent, you just need to be over like 2 or 4,000, 4,000 really. So this is totally fine. If we do this again, we do it a second time for this location, you can see that the velocity went up by a factor of 4, 18.3. The diameter went down by a factor of 2. Okay, but the viscosity is the same, so it's still gonna be, in fact, it's gonna be twice the Reynolds number. Okay, because this went up by a factor of 4, this went down by a factor of 2. So all told, it's gonna go up by a factor of 2. We can ascertain that by doing 18.3 divided by 12 times, okay, divided by 1.4 exponent -5. Okay, and we'll get 10.9 times 10 to the 4th. Okay. Obviously, I'm not even using scientific notation because I wanted to make it clear that that was just double the other one. So anyway, so alpha. So we use all that to say that alpha does in fact equal 1.0 or 1.05, but you know, your book likes to make you use 1.07 or 1.03 or something. Just use 1. Okay. I mean, it's so standard that, you know, I have to admit that when I first started reteaching this, I didn't even remember that alpha was there. I still think, you know, your first time through this course, it's probably a good idea to remember to solve for the alpha, just in case you guys ever get into a problem, you know, when you're actual engineers and for some reason you end up in a, you know, in a laminar flow situation. Probably won't happen very often, but just in case you'll remember that that correction is there. All right, so, oh great, I erased all that. What were my numbers? I think it was like 4.55. Is that right? Anybody?
I'm not sure. I think I lost it too.
You talking about velocity or the?
For the velocity, yeah.
I think the other one is 4.587 something.
587.
Yeah.
Maybe we'll just call it 4.58. You know, let's see if I got it. Oh yeah, I got it. 4.58.
73, something like that.
36. Okay, feet per second. I know I'm a stickler for these things. Yeah, I don't know why I'm plugging in numbers right now, but I guess I am. 32.2 feet per second squared. Okay, plus HP. Okay, so I guess, you know, we've got that. This is what we're looking for right here. P2 minus P1 over gamma naught.
93 point.
Yeah, let me erase that and let's okay, what was it? 93 point something?
Yeah. 93.4.
1512.
512.512 minus H. Okay. And this always happens. These two H's always cancel each other out, which is like a really nice thing, but it's just something to, you know, watch out for. And then we'll get the V2, which is 18 point, whatever. Come on, where are you? Clearly I've done this because, 18.334. So 18.334 feet per second squared over 64.4 feet per second squared. Okay, so these H's are going to cancel, okay, which is nice. Like if that doesn't happen, then you're kind of like, you're either thinking, well, Wagner needed to give me that, or I've made an error somewhere. Okay, so HP ends up being, I'm actually, you know what, I'm gonna leave these things alone for a second because I always like to make this point if I can. Let's see here, 4.5836 squared divided by 64.4 is, so 0.326.
The AP is 52 point something.
What's that?
I think the AP is 52 point something.
Oh, you already solved it? Well, let me I just wanted to make one point here. So 3, whatever that number is, 4 squared divided by 64.4 equals 5.2195 feet. Okay, so well, check my calculation because I'm not getting in the 50s. I'm getting something in the, looks like in the almost at 100.
All right. What's my note?
Maybe I made an error. But anyway, one of the points that I wanted to make here is, okay, so area here equals, or I guess I would, so I'm going to compare D1 and D2. So location 1 versus location 2. Okay, diameter. Okay, location 1 has 2 times the diameter of location 2, right? So that means that location 2 has 4 times the velocity, or I guess area. That means that this one's got 4 times the area, 4x, right? Which means for velocity, location 2 now has 4 times the velocity, right? Now, then when it comes to head, right, we have to square these velocities right here and right here. We have to square them. So when we square them, location 2 ends up with 16 times the velocity head over 2g. I can't really write the 2g down there. Okay, 16 times the velocity head. So small differences in these in the pipe areas, I guess it's a factor of 2, leads to massive differences in the head. So like if I were to take that 0.32 and multiply times 16, I'm going to get this number right here. Okay, so it's just important to recognize that when you speed that water up, it means from an energy standpoint, this one is almost like you could almost ignore this one if you wanted to. It's not really important. Okay, now for this class, don't ignore it, but it's just something to kind of be aware of and get some intuition. So Bull, did I make an error or did you make an error?
Well, you use the Q as I got a different number from like the velocity. Like B1 I got 45 and B2 got 183.
Okay, because you used for your Q you used 1 CFS.
Yeah, and then AP is 582.907.
Right. Okay, that makes sense. Yeah. So that's why. So you just used a different number for Q.
Yeah.
All right. So if we use my numbers though,
I would say so.
yeah, it's fine. So I'll do 93.512 plus 5.2195 minus 0.32623. And we get HP equals 98.405 feet. Okay, so now we can go back up here to this and we can just solve this problem, right? So we can say, okay, well, that's the pump gives it 98.4 feet of head. So how much power are we supplying? This is to fluid, to the gamma. Remember, and so this is the careless error I would make. And if you look at my keys, I make this all over the place. Is, I'm home free. So forget that the gamma here is the gamma of oil. So I need to do 0.82 times the gamma of water, 62.4 PCF, times that HP, 98.405 feet, times Q, which is 0.1 CFS. Okay, and then of course I always recommend checking out your units. So the pounds per cubic foot. So we've got cubic feet here, we've got cubic feet here, so those cancel. And left with pounds, feet per second. Okay, which is a good unit for power. Okay, so we just multiply that. Okay, times.
And the arrow too. I didn't.
What's that?
I say I made the same arrow like the one you just mentioned. Like you got to multiply by 0.82.
Yeah. Yeah, I make that error. To me, it's the most common. It's probably the most common error I will make. So 503.52 And that's foot-pounds per second, foot-pounds per second. And if you get a really big number and you hear you don't like it, you can divide by 550 and put it in horsepower. I don't like horsepower because the unit, well, I like horsepower because it's a nice small number, but you can't use it in your equations. So you always have to convert back to foot-pounds per second. But the other reason that I don't like it is its symbol is HP, which in a problem where you're working with head for a pump, that can be confusing. So, I would just generally try to avoid that. Now you might in the next class, like if y'all are in hydraulics, they might ask you to solve for a problem and just get it into horsepowers. And if they want you to do that, just divide by 550. But don't have anything to do with horsepowers other than that. Or if they give you a problem in horsepowers, just multiply by 550 foot-pounds per second. So, unfortunately, in America, we do this the dumb way. So, we just got to deal with that, the dumb units sometimes. So, hey, Bull, in Sudan, what units do you guys use?
kg.
What's that?
I said we use like kg, and we use like
Yeah.
Yeah.
Yeah. Y'all do it intelligent. Y'all do height too, and like short distances. Y'all don't use feet or inches for anything.
No, we just use like meters and stuff.
Okay. Yeah, because it's really confusing if you go to England. And they're like it is the English system of units, and they use kilograms and things like that. But sometimes they use inches and feet and things like that. It just depends on what it is. Or like I found a scale and I wanted to weigh myself, and it told me how many stone I weighed, and I was like, what? I have no idea what it means. And I think it was
Don't they sell gas in liters also?
They do sell gas in liters.
Yeah,
That's fine. I know what a liter is for the most part, but a stone I had to look up. I think it's either 14 or 18 pounds per stone. And then, so anyway, what's up, my boy? What's up?
That's the same in Sudan too. Like when they sell a gas, they do with a liter because I think most of it because the Sudan was colonized by the England. Mm-hmm. So we follow almost what they did.
Yeah. Well, yeah. As long as you end up with kgs, all I can say is that's it, man. I wish we'd done it. They started to try to I think in the 70s they started to do something where they were going to slowly shift everybody over, but then they didn't do it. My dog is going crazy. What is it?
Your dog need to do some homework.
Okay, let me come here. Come climb up on me. All right. Anyway, okay, so I'm going to do the third problem from this exam. I have an object with a mass. This is what's given. Mass equals something, and a volume equals something. Okay, so the mass is given in slugs. If I drop this object into seawater, if I drop this thing into seawater, which has an S of 1.03, okay, will it float or sink? Okay, so the required is float or sink. Yeah, that's the first question. And then the second question is, I would like to make this object neutrally buoyant. Okay, to make neutrally buoyant. Okay, so what we're going to do is we're going to either add a balloon or a weight. Balloon or weight. And then if I attach a balloon, so then if I add a balloon, how much volume does it need to be? If I add a weight, what does the weight need to be in order to make this thing neutrally buoyant? And when I gave them this problem, I said, if it ends up being a balloon you need to add, I want you to ignore the weight of the balloon. And if you add a weight, I want you to ignore the mass of ignore the volume of weight. Okay. So this is an interesting problem because depending on what your student ID number was, it would either float or sink. Everybody, well, I'm assuming roughly half the class went up and half the class went down. Well, let's pick something that will almost certainly sink. It's hard for me to actually think about these numbers. let's give something that's 3 slugs. Let's make it 3 slugs, and we'll work this problem twice. So that we can see both ways, both things that can happen. Make this 0.5 cubic feet. Okay, you're kind of like, well, I don't know what that's going to do. Okay, so what we want to do here is we want to compare the density of the object to the density of the seawater, or it could be the specific gravity, the specific weight, or whatever it was. We know the specific gravity of seawater here. So we could go ahead and just try to get the density of this thing. So S of our object equals the density of our object divided by the density of water. Okay, so that's really the way we're gonna approach this, and we're gonna compare this number to that number. Okay, and if the S of the object is greater than the S of the seawater, then it's gonna sink. Okay, so let's go ahead and do this. The density of the object is well, that's the mass, 3 slugs, divided by the volume, 0.5 cubic feet. Okay, divided by the gamma of water. Now the gamma of water, this is annoying, right? Because whenever you have to deal with, excuse me, not gamma, the rho of the water, the density of water is in slugs per cubic feet. So that's 1.94 slugs per cubic feet. Okay. And hopefully you can see how I knew that this thing was going to sink. Okay, so 3 divided by 0.5, that's 6. So 6 divided by 1.94 is about, 3 point something. Oh, 1.94, yeah, 9492. 62.4 divided by 32.2, 1.94, okay. 6 divided by 1.94 is 3.0928. Okay, so this is almost 3 times as dense as the seawater, so it will sink. Okay, so if it's going to sink, then we're going to have to add a balloon to it to make it rise, or to make it not sink. So then the key is, how big does this balloon have to be? So, well, let's see. So here's our object. It's underwater. So here's our free body diagram. Hey. What's going on? Hold on, give me 1 second. Let me see. What is it that you want out there? You want to eat some grass? We'll go open the back door for you. Come on. Sorry about that. Some days are just too pretty to be, stuck inside while your master works. Okay. Anyway, okay. So, so our free body diagram looks something like, we've got this object, and the object's got a few things going on. It's got a weight, and it's got its own buoyancy force. And it's got a balloon, because we have to add a balloon to it. And the balloon has a buoyancy force. So F, buoyancy, balloon. Okay. So for this thing to be neutrally buoyant, that means all those things are going to add up to 0. So we're going to go ahead and do FB plus FB minus the weight equals 0. Technically, there's also a weight of the balloon. Like if we drew this all as one object, so if this is the weight plus the balloon, if this is the 2 objects here, then the weight of the balloon would also be on here. But I asked you to ignore the weight of the balloon, basically because I didn't want you to have to think about that too much. So so the buoyancy of the balloon. So buoyancy is always gamma of the fluid. So that's seawater in this case. Seawater times the volume of the balloon. which is what we're solving for right here, plus the buoyancy of the weight, which is going to be the gamma of seawater, plus the volume of the object, okay, which was given, object, minus the weight of the object, which of course is going to be mass times gravity in this case, equals 0. And so that's ultimately how we're going to solve this, because we know the gamma of seawater is what, 3.0928 times the gamma of water, which is 62.4 PCF, times the volume of the balloon plus, well, let's do it this way. Volume of the balloon plus the volume of the object, which is 0.5 feet cubed. Okay, minus the mass, which is 3 slugs, times gravity, which is 32.2 feet per second squared equals 0. Okay, by the way, if you solve this and you end up getting a negative volume, then that means you made a mistake here probably. Well, I mean, you could have made a mistake on your algebra, but if you end up getting a negative volume, then that means basically, you got the wrong sign on this, which means you should have added a weight. All right, so let's see, 3 times 32.2. Okay, so bring that over to the other side, make it positive, divide by 3.0928, divided by 62.4. Whew. Subtract 0.5. And I got a really small balloon. I might have made an algebra error here. My balloon is like 5.42 times 10 to the negative 4 cubic feet. Anybody else get that same number? 3 times 32.2. I mean, divided by 3, divided by 62. Yeah, it's just a really small balloon. Guess that's how it goes sometimes. Okay, small balloon. Okay. I guess I should have made it more dense if I wanted to get a bigger balloon. So we can go the other way. Just to give you an idea, if I went the other way and I made this number small, 0.1 slugs. Okay, we could do the exact same thing to compare. I'll go down here and I'll go ahead and put in a 0.1. So this would be if you had a different student ID number, right? So 0.1 divided by 0.5, that's 0.2 divided by 1.94 equals 0.1. 0.10309. Okay. So now we know this thing is going to float because the specific weight or the specific gravity of the object is less than that of seawater. So let's go ahead and erase this. So now instead, in order to keep making neutrally buoyant, we're going to have to add a weight. Weights are actually nice because I think they're a little bit easier. So we'll add a weight of, so this is the weight of the object, and this is the weight added. Okay, so same concept. To be neutrally buoyant, everything has to add up to 0. So we'll say force of buoyancy minus the weight of the object minus the weight added equals 0. Okay, so the force of buoyancy is what? That's S of the water, seawater, times the gamma of water. Okay, so that's the gamma of the fluid times the volume of the object, since it's a volume displaced, which in this case is completely underwater. Okay, minus the weight of the object, which is the mass of the object times gravity, minus the weight added. Okay. Again, if you get if you get a negative number for the weight added, you've got the wrong. You did it wrong. So I'm just gonna. I guess I'll just punch these numbers in. Well, I'll go ahead and write them in. S of seawater is 1.03 times the gamma of water, which that's 62.4, times the volume of the object. What's the volume of the object? Oh, a half a foot, half a cubic foot. Okay, minus the mass of the object, 0.5. Oh, no, 0.1 slugs times 32.2 feet per second squared, minus the weight added equals 0. Okay, so we just go ahead and solve that. So 1.03, yeah, 1.03 times 62.4 times 0.5 minus 0.1 times 32.2. Oh yeah, so we're gonna get 28.9 pounds. Now I'm wondering, did I use this number last time right there? I didn't use 3 point. Oh, 3, it would have been.
Use 3.
Yeah.
Right, but it should have been 3. Well, you're right. For the seawater, it should be, make sure that for the seawater, I used 1.03. And not for the, did I do it right?
I think I might have written down wrong because I used 1.03.
Oh, well, yeah. So if it's for the buoyancy force is always about the fluid. So the buoyancy force should be related to this 1.03. So just check your notes and make sure that the last time through that I used that right number.
All right.
Okay. Okay. So what we got? We got 30 minutes. Let's, any questions on this? The buoyancy problems are always just, draw a free body diagram and figure out what you're looking for. The only way that I ever play with this, and this one was a little bit unusual, but usually what I like to do is I like to have something where only part of it is submerged. So that you just, because what I want you to know right here is that it's only the volume that's underwater. So this is actually the volume displaced. So it's only this volume. It does not include this volume. Okay, so just, something to be aware of. Okay, so, yeah. Anyway, let's see, on to the next one. Let's do this. Oh, okay. Draw the EGL and HGL for the system below. This one was designed to be easy, but I also knew that because of the way I drew it, it was going to trip some people up. But if you knew your stuff, this was like a really easy problem. Okay, so imagine those lines are vertical. The vertical lines are actually vertical. Okay, and so we've got water here, and I don't know, somewhere over here. So what I said is, this one was given, and what you're supposed to do is draw the HGL and the EGL, and then indicate with the star the location where cavitation is most likely. Cavitation is not very likely on this system, but I guess it depends on how you draw it. It could happen. So, so what we're going to do here is, okay, so, well, let's do it. Okay, so the key here is this. We're going to lose energy here, here, and here. Those are our minor losses. Okay. Other than that, we're just going to lose on the walls of the pipe, and we're going to lose water. We're going to lose energy faster here than here because the pipe is narrower. Okay. So basically, if I keep that in mind on the instructions, I told you to do it in, dotted and solid, but I think here, there's no need for that because I have colors, so here's black. I guess black's a terrible color for this. Do we have a green? We've got a green. Okay, so here's green. This is the HGL. Okay, so we're gonna lose a little bit right there. We're gonna go down fairly steep here. Okay, then I'm gonna hit this point. I'm gonna lose some energy. Now I'm gonna go down less steep because I got a wider pipe. And then there'll be some energy loss here. And that's it. That's the EGL. Okay, and if I'm grading it, what I'm looking for is I want to know that this is steeper than this. And I'm going to check to see that you've got these losses. And that you end up on the water surface. So that's how I would grade the EGL. For the HGL, then we would do, we're basically kind of doing V squared on 2G in our head. So V squared on 2G. So where is that the biggest? It's the biggest in this pipe, and it's the smallest in this pipe. Okay, so I've actually already kind of decided how big it's going to be because this loss right here is V squared on 2G. So that means basically, and this pipe has a constant diameter, so that V squared on 2G is not going to change through that whole length. Right, something like that. Okay, now it goes into this narrower pipe, so the V squared on 2G needs to be bigger. Okay, and you know, have fun with it. There's no reason to be afraid. You can go pretty big. And then there you go. Okay, and that's it. I mean, there's only 2 V squareds on 2G in this whole thing. There's this one, narrow pipe, this one, wide pipe. Okay. Now this little, you know, discontinuity kind of troubles people sometimes, but what's happening basically is right there, we're having energy convert from velocity to basically pressure, right? It's becoming pressurized because the pipe widens. Okay. So that's what's happening here. The pipe is widening, the fluid slows down and it becomes pressure rises. And so that's what this little, like that little jump right there is, the jump in pressure. Okay. So if you wanted to know where is this thing most likely to cavitate? Well, let's see here. So in black, you know, here's a random datum down here. Well, here's our Z. Z. Usually if you're going up in a flow, if the flow is going upwards, you know, pressure's dropping. So you know, be aware of that. And that will kind of help you figure out where it's most likely to cavitate. Or where, you know, we're basically looking for where is the pressure the lowest. Okay, we know V squared on 2G, I've already put that in a couple places. Okay, this is V squared on 2G. So what's between those two is the P on gamma. So the P on gamma, I don't know, maybe we'll do that in green. That's right here and here. And you can see it's getting smaller and smaller and smaller. And it even goes negative a little bit maybe. And then it goes back to being positive. Okay, so the most likely place for you to cavitate is like, so let's see, if I do Z going right up maybe to here, then it might even be negative right in there just a little bit. You know, it might go from there back down to that blue line. Okay, so basically, you know, I would be looking for a star somewhere right in here to say that's where cavitation is most likely. Okay, and it conceivably could happen. So like if I had drawn this thing, you know, if I'd drawn this pipe and had it go way up here like that, you know, then you can see that, you know, the pressures can get quite negative if you try to go too high. So, you know, just something to be aware of. Another possibility, and I hadn't really mentioned this, is, I don't know if I can, let me undo that. Is all right, so let's suppose we're looking at this spot right here. And you're like, well, it's not going to cavitate, but it will have low pressure. So one thing to consider is that, let's suppose your pipe has low pressure. Let's suppose it goes negative. So what that means is that, you know, because people tend to freak out about that, and because we forget about gauge pressure, is it just means it's lower than atmospheric pressure. But if it's lower than atmospheric pressure, that means the pressure on the outside is greater than the pressure on the inside of the pipe. So if your pipe is made out of like, I don't know, some like, you know, soft rubber or something, then you have a possibility that your pipe might just implode. Okay, so it's just something like, if that's going to happen, you want to be aware that your pipe needs to be strong enough to, you know, maintain the outside pressure, or the difference between the two, really. I guess normally it is because I guess normally the pressure is higher on the inside than it is on the outside. And so you kind of, you assume, I think you usually assume the pipe can hold that, or you size the pipe for that. But just be aware that, the other possibility can happen if the pressure on the inside of the pipe drops too low. Okay, so any questions on this? I mean, I guess the only thing I could have done to make this, test you a little bit better would been to put a pump or a turbine in there. Other than that, I mean, I can make it complicated. I can have a whole bunch of different changes in the pipe diameters and things like that. But this really answers all the questions that I have for you, like, theoretically, or not qualitatively. Now, if I wanted to make it quantitative, which I probably won't do, we can make it a lot more complicated. But
Oh, so on the final, we'll just have to draw something. We won't have to like solve for anything for the
probably. If you look at the old finals, I've done some where I draw it for you, and then I ask what's going on. So like if I erased the diagram of the water and the pipes, and I could say what's happening here. Now you wouldn't be able to tell, for example, that this pipe is going up. Like you wouldn't be able to tell that come on, man. You wouldn't be able to tell that the pipe was climbing right there. There's no way to tell that from this drawing. But you can tell, you could say like, I could say like, what's happening here? And you can say, oh, well, the pipe's expanding, and something about how they're connected, the two pipes are connected is a change. So there's a little bit of a loss here. So it could just be that it's doing this, and then it did like that, and that would draw exactly the same way as I just drew it. Right. So, or you could say like, what's going on right here? Well, the fact that these two are at the same height means that this is a reservoir. And the fact that this just dropped like that means it's kind of an abrupt loss of energy, an abrupt expansion. Because otherwise, usually if the expansion is not abrupt, usually you'll see something like that. Or, I mean, there's lots of different ways it can happen. I think one of the ones that we did in class, I think it looks like this, which is pretty weird. But anyway. Okay, so does that answer your question, Max?
Yeah, thank you.
Okay, cool. Okay, hold on, I gotta. Oatmeal's really not good. I mean, like it's totally okay to just have around the house for an emergency, but boy, it's not really my favorite.
Unless you put like a whole lot of fruit in it or something.
Right. But then it's really just because I like the fruit,
Yeah.
All right, so let's see. Let's see. I got 3 left on this thing. We got like 20 minutes. So y'all pick. I can either do determine the force P necessary to just start opening the 2-meter wide gate. I could do this one. Looks like it's a momentum problem. Or I could do find the discharge of water through the pipe, blah, 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 with loss coefficients.
I would say the second one because
Momentum?
the harder of the two.
Okay. Then you think like I do, which is that the momentum is the hardest, but I don't always get that response from people. Okay, this will be number 6. Okay, let's see here, number 6 off of that test. I guess it doesn't matter, you don't have the test. So anyway, given, I'll draw the picture. Picture is easy. And this makes an angle of 30 degrees. And it's got the Q going this way. Oh, and it's got X, Z. Okay, 1 meter diameter pipe. Carrying liquid magma. I like that, liquid magma. S equals 2.65. Okay, with a steady flow rate of Q equals, looks like this was something based on your student ID number, so 5 CFS. Oh, CMS, excuse me, cubic meters per second. Come on. CMS. The bend turns downward at an angle of 30 degrees. The volume of the magma in the bend, so volume of magma, is some number of cubic meters. Can't believe I gave that to the class. Normally I would make them calculate that. You know what? Let's make you calculate that. Let's assume we don't know that. Let's assume that what I will give you is I'll say the length of this thing. Come on, you can do it. The length of this is, I don't know, 5 meters. Okay. And the empty weight of the bend, so the weight of the bend is 2.4 kilonewtons. Assume the pressure in the pipe, pressure everywhere, is 75 kPa. 75 kPa. What is the vertical force required to hold? So the vertical force to anchor. So F anchor in the Z direction equals what? Okay, so this is a momentum problem. And of course, the reason I assigned it the way that I did is, I said, well, I want you to do the Z direction. I'll almost never ask you to do the Z and the 2 directions. I did that once and it ended up just taking the class entirely too long, and there was nothing to be proven once you knew 1 direction. So I guess, just that you can add forces in 2D, which I assume everybody should be able to do already anyway. So what we're going to do here is, let's see, we're going to do a free body diagram of the pipe and the water. So here it is. Okay, and now I need, let's see, so in blue, here's my momentum fluxes, 1 and 2. Now I need forces, I'll do them in green, P1A1, or P2A2 right here, and P1A1 right here. Okay, and then we've got weights. So I've got the weight of the bend. I've got the weight of the magma. And then I've got the force on the pipe. So F anchor Z, and F anchor X. I'm actually going to call this FAZ because I don't feel like writing the word anchor out a million times. Although, if ever you get into coding, somebody once pointed out to me that it was better to just write out the full word. And boy, was that correct. Okay? It's better to make it clear than to make it short. So P2A2, this is P1A1. Okay, so let's go ahead and get started. And so this is in the Z direction. So our equation is going to look like this. Sum of the forces in the Z direction plus rho VQ in, really the sum of those, right? So in this case, there's only 1, equals the sum of rho VQ out. And the key here is to remember that, I'll just make them in green. Vectors, vector, vector. Okay, everything else is a scalar. Okay, so let's start with the forces, and what we're going to do is just straight out of statics. Okay, so let's see, we've got FAZ, that's a vertical force. We've got minus the weight of the bend, minus the weight of the magma. Yeah, I remember when I was making this, I was trying to think of another fluid we could use. Clearly, I don't really know that we move magma through pipes. So let's see, vertical force 1, 2, 3. We've also got this P2A2 plus P2A2 times the sine of that angle. I'll just call it theta for now. And then this poor dog is, and then in, okay, so in the X direction, I mean, we have 1 going in, but in the Y direction, we don't have 1. So we're just gonna ignore that term. So we're gonna equal for the outs, I'm gonna have the rho of the magma, which will be S magma. Or I guess we'll call it S sub M for magma. Rocky, please don't destroy that ball. I don't want to buy you another one. Okay, S magma times the rho of water. Okay, now we got the VZ, okay, or in this case, V2. So that's going to be, let's see, that's downwards. So it'll be minus V2 sine of theta. And then we're going to multiply that times Q. Hey, don't eat that ball. Do not eat that ball. Okay. So, and so that's how we're going to solve this. And, you know, what we're looking for is FAZ. So let's go ahead and let's do it. Okay. So I think we'll probably need one more row to get all the things in here that I want. So the weight of the bend, well, we know that, so that's good. Weight of the bend minus the weight of magma. Well, the weight of the magma is going to be the gamma of magma. So S magma, gamma of water. Okay, times the volume of the magma, which is going to be the area of one end, pi times d squared on 4, times the length of that pipe, which will be 5 meters. So we'll just call that L. Okay. And then plus P2A2, so that's P2 over pi d squared on 4 times the sine of the angle equals, it looks like S magma rho water minus B2 sine theta times Q. Okay, so I guess the only thing we need to solve for all this is just get the velocity through that pipe. So get velocity by doing Q over A. So that's V1, V2, whatever. So V is 5 cubic meters per second divided by pi, 1 meter squared over 4. Okay, so V equals whatever that number is. 5 times 4 divided by pi. 6.33, excuse me, 6.3662. And that's meters per second. Okay, so I think at this point, it's just a plug and chug. Let's just go ahead and check that. FAZ minus the weight of the bend, 2,400 newtons minus 2.65. By the way, 2.65 is the density of like a sand. So that's how I chose it for magma. I would assume magma is probably a little bit less dense than sand, but I'm not sure. Okay, gamma of water is 9810 newtons per meter cubed. So pi times 1 meter squared over 4. Length is 5 meters. Okay, the units we'll get newtons out of that, so that's good. Plus P2, 75,000 newtons per meter squared. Times pi times 1 meter squared over 4. Times the sine of 30 degrees. Sine of 30 degrees is a half. Equals S magma 2.65. Gamma of the rho of water, which is 1,000 kilograms per meter cubed. Okay, this is also the thing that stinks most about this equation is that it usually has gammas and rhos, so you have to kind of be careful. You know, so here's a gamma and here's a rho. And then we've got negative V2, which is 6.3662 meters per second, times the sine of 30 degrees times Q, which is 5 cubic meters per second. Okay, so let's see, FAZ minus 2,400 newtons minus 2.65 times 9810 times pi divided by 4 times 5 is, oh, big number, 102,088. That's one more sig fig than I like, but whatever. What was that? That's the weight of the magma. Okay, plus, this is what happens when you just make problems up. Let's see here, 75, 123 times pi divided by 4 times pi divided by 4 times the sine of 30. Okay, so we get 29,452 newtons equals whatever all this stuff is. So 2.65 times 1,000 times 6.3662 divided by 2 times 5 equals, no, don't, what just happened? No, don't do that. Oh, here we go. Sorry, equals 176 newtons. Okay, so even though this problem is made up, and so these numbers are not necessarily realistic, I think it's always a good idea to step back and just kind of look at the size of things. Like if you were doing this in an engineering job or something, you'd want to step back and not just plug all this number stuff into your calculator to get FAZ, but it's also nice to say like, well, what really matters here? Clearly this 2,400, even though I made the numbers up, the weight of the bend is not important. Okay, the thing that stinks right now is just carrying the magma itself, and there may not be anything you could do about that. You might be like, well, I'm trying to move this magma from point A to point B. Can't really do a whole heck of a lot about that. The pressure term and the momentum term, they matter, but it's really the weight of the thing that really is killing you. So anyway, oh, sorry, this is supposed to be a negative number, right? So let's go ahead and get an answer, even though, like I said, I made all this up. So minus 29,452 plus 102.088 plus 2,400. Okay, so unless I did it wrong, this is 32.9 kilonewtons, and that's got a positive sign. So basically, we're gonna have to push up with 32.9 kilonewtons to keep this thing from falling. Okay, so that's cool, right? So basically, the pressure is helping hold it up a little bit. The momentum is helping to propel it up a little bit. This doesn't really matter. And then, but ultimately the weight is winning out. So we still have to support about a third of the weight. So, so that's not bad. Anyway, I think we're out of time. So any questions? Is this logical? I don't know. At some point towards the end there, we just plug and chug. But any questions? Okay, well then I guess we're good. I'll see you guys when I see you. So I'm giving a statics exam on Monday. And so all next week I'll have office hours, normal times. So, and I'll probably set up, I think our final is on the following Monday, I think, or maybe it's on Tuesday, I can't remember. But I'll probably set up some special, if you have any problem with studying and you just need some extra help, and obviously if you want to contact me and just because you're like, on a random night, that's fine too. So anyway, thanks guys.
Thank you.
All right. Have a good week or weekend, I guess. God, it's finals time, so no one's having good weeks. And recording.